When you culture cells in a standard Petri dish, they grow in a flat, random scattering. Contrast this with native skeletal muscle, which consists of a highly structured, parallel array of three-dimensional fibers. Replicating cells in a two-dimensional monolayer produces a cellular slurry. It fails to produce actual meat tissue because the cells lack the physical architecture required to align and mature. Animal cells require a three-dimensional extracellular matrix, or ECM. This matrix provides the necessary mechanical support and spatial cues for directed cell growth. This reliance is driven by mechanotransduction, the process by which cells sense physical forces and translate them into biochemical signals. Adherent cells, like myocytes, require strict physical anchoring to survive and differentiate into functional muscle fibers. Replicating the precise sub-micron topography of the native ECM is the primary biological bottleneck preventing the scale-up of cellular agriculture. Pacing picks up. Electrospinning is the premier fabrication technique for solving this geometry problem. High voltage draws a liquid polymer jet through the air, depositing it as a dense web of nanofibers. This process accurately reproduces the scale, porosity, and interwoven architecture of the native extracellular matrix. There is a critical flaw for food production. Traditional biomedical electrospinning relies on highly toxic solvents, like HFIP, to dissolve synthetic polymers. Biomedical tissue scaffolds are structurally perfect for cell growth, but they cannot legally or safely be consumed as food. To commercialize cellular agriculture, engineers must discard the toxic chemistry and recalibrate the physics of electrospinning, using strictly food-grade biopolymers and green solvents. An electrospinning system relies on three basic components: a charged syringe containing a polymer solution, an applied electrical field, and a grounded collector plate. Applying high-voltage electrostatic forces to the liquid causes it to overcome its natural surface tension and bulge outward. When the electrical stress reaches a critical deformation threshold, the droplet snaps into a geometric shape known as the Taylor cone. A charged polymer jet is then ejected from the apex of the Taylor cone, whipping across the gap toward the grounded collector. Inside that liquid jet are floating polymer chains. Their physical density in the solvent is measured against a threshold called the critical entanglement concentration, or CE. Below the CE threshold, the chains act as isolated coils. The elongational strain from the electric field causes the jet to fracture midair into bead-like defects, a physical failure known as Rayleigh instability. Above the CE threshold, a transient three-dimensional network of physically entangled chains absorbs the strain, allowing the stream to stretch into an unbroken, solidifying fiber. Weaving a continuous nanomatrix requires precisely balancing the applied electrical voltage against the internal polymer entanglement. During the jet's microsecond flight from the syringe to the collector, the solvent carrying the polymer must rapidly evaporate. Toxic biomedical solvents evaporate instantly. Contrast this with food-grade alternatives like ethanol or acetic acid, which have highly sluggish evaporation kinetics. Substituting these green solvents alters the liquid's surface tension and dielectric constant, destabilizing the Taylor cone. If evaporation is incomplete, wet fibers hit the collector plate and melt into a solid film. This destroys the critical nanoporosity required for cell infiltration. To force green solvents to work, engineers must adjust the working distance, the liquid flow rate, and the ambient humidity. Implementing edible solvents requires a total recalibration of the system's electrohydrodynamic physics. The structural materials themselves must also shift from animal-derived gelatin to plant-based alternatives. Gelatin contains intrinsic RGD amino acid sequences that naturally promote cell adhesion, but it is structurally weak and directly conflicts with the animal-free goals of the industry. Plant-based prolamine proteins like corn zyme and various polysaccharides offer highly stable food-grade candidates. The current engineering compromise is that plant polymers often lack sufficient natural entanglement. They temporarily require synthetic carrier polymers, like polyethylene oxide, to stabilize the electrospinning jet. The resulting physical structure dictates cell behavior. Achieving submicron fiber diameters provides a high surface area to volume ratio that directly enhances cell proliferation rates. This chart illustrates how substrate stiffness controls cellular identity. If the scaffold's elastic modulus is tuned specifically to the 8 to 17 kilopascal muscle target zone, cells mechanically trigger to differentiate into muscle tissue rather than bone or fat. The biopolymer recipe dictates the scaffold's physical structure, and that structure directly programs the biological identity of the cultured tissue. The scaffold can also function beyond a passive structural skeleton, acting as an active biological delivery system. Supplying necessary growth factors entirely through ambient liquid culture media places a massive economic burden on production facilities. Coaxial electrospinning is used to build complex, multi-layered fibers simultaneously. A dual nozzle extrudes an inner liquid fiber entirely encased within an outer liquid shell. Growth factors and sensitive bioactives are encapsulated within the fiber's core. This ensures a controlled, localized release directly to the attached cells. Coaxial fibers erm the extracellular matrix into a dynamic, nutrient-delivering network, drastically cutting the reliance on expensive bulk media. Moving out of the laboratory requires adapting to the massive physical scale of commercial food manufacturing. Single-needle electrospinning systems yield a mere 0.1 to 1 gram of material per hour. This microscopic throughput mathematically prevents cultivated meat from reaching mass-market grocery stores. The mandatory industrial step forward is needleless, or free-surface, electrospinning. A rotating cylinder submerged in a polymer bath generates dozens of simultaneous Taylor cones upward across its surface. This architecture pushes production yields from fractions of a gram to over 90 kilograms per hour. Mastering multi-jet free-surface electrohydrodynamics is the definitive physical threshold separating lab experiments from commercial reality. The final hurdle is proving to government oversight bodies that these engineered nanostructures are safe for mass human consumption. Regulatory agencies do not automatically grant generally recognized as safe status to novel physical forms of already approved ingredients. The extreme electric fields of electrospinning alter a polymer's chain orientation and crystallinity. This necessitates entirely new proofs of safety and digestibility. Rigorous analytical frameworks, specifically gas chromatography mass spectrometry, are required to prove the complete absence of trace green solvents. Thermal gravimetric analysis is necessary to map the scaffold's thermal stability during consumer cooking processes, specifically tracking interactions with the Maillard reaction. Future facilities will integrate inline process analytical technologies to monitor fiber morphology in real time on the factory floor. The viability of cellular agriculture depends on this interdisciplinary mastery, fusing material science, electrohydrodynamics, and food engineering to scale sustainable protein for the world.